Thermal transducers is a device in an automatic temperature control system that converts the temperature into some other quantity such as mechanical movement, pressure, or electric voltage. This signal is processed in a controller and is supplied to an actuator which controls the heat of the system.
Thermistor is, as the name implies, a temperature-sensitive resistor. That is, its terminal resistance is related to its body temperature. All resistors vary with temperature, but thermistors are constructed of semiconductor material with a resistivity that is especially sensitive to temperature. Thermistors are nonlinear devices. However, unlike most other resistive devices, the resistance of a thermistor decreases with increasing temperature. That's due to the properties of the semiconductor material that the thermistor is made from. The symbol of a thermistor is represented as this. It is not a junction device and is constructed of germanium, silicon, or a mixture of oxide of cobalt, nickel, strontium, or manganese. The compound employed will determine whether the device has a positive or negative temperature coefficient. The thermistor categories are the NTC, or the negative temperature coefficient, and the PTC, positive temperature coefficient thermistors. The negative temperature coefficient, or NTC, thermistors has the property where the resistance decreases with increasing temperature. The NTC thermistors are made from a disc or cast chip of a semiconductor. The PTC thermistor has the property where the resistance increases with increasing temperature. Most PTC thermistors are of the switching type, which means that the resistance rises suddenly at a certain critical temperature. The characteristics of a thermistor with a negative temperature coefficient are provided in the figure. At room temperature 20 degrees Celsius, the resistance of the thermistor is approximately 8,000 ohms, while at 100 degrees Celsius, the resistance has decreased to 100 ohms. A temperature span of 80 degrees Celsius has therefore resulted in 50:1 change in resistance. It is typically 3% to 5% per degree change in temperature. Here's a simple temperature indicating circuit. Any increase in the temperature of the surrounding medium will result in a decrease in the resistance of the thermistor and an increase in the current IT. An increase in IT will produce an increased movement deflection, which when properly calibrated will accurately indicate the higher temperature. The variable resistance was added for calibration purposes.
Good afternoon, everyone. I'm Juan Pocholo Idalmundo of Group 2, and I was assigned to discuss about the RTDs. RTD means Resistive Temperature Detectors, or also called as Resistance Thermometers. An RTD utilizes the relationship between electrical resistance and temperature, which may be either linear or non-linear. RTD are sensors used to measure the temperature using the resistance of a wire. When a metal wire is heated, the resistance increases. RTD normally uses a wire of film of platinum, nickel, copper, or nickel iron alloys. There are two main types of RTD, traditional RTD and thermistors. First one is the traditional RTDs. It uses metallic sensing elements that results in a linear relationship between temperature and resistance. The second one is the thermistor. It uses a semiconductor sensor which gives a power function relationship between temperature and resistance. Next is I'm going to discuss about the structures of an RTD. Here is a diagram of a resistance temperature structure. This layer of an RTD is the outer sheet. Next is this part is the insulator. These two wires here are the connection leads. And lastly, this is the resistance sensor. The outer sheet here prevents the contamination from the surrounding medium. Ideally, this sheet is composed of material that efficiently conducts heat to the resistor, but resists degradation from the heat or the surrounding medium. And the resistance sensor itself is responsible for the temperature measurements. There are four major categories of RTD sensors: the carbon resistor, the film thermometers, the wire wound thermometers, and the coil elements. First is the carbon resistor. They are the most commonly used sensors. They are inexpensive and are accurate for low temperatures. Second is the film thermometers. They have a very thin layer of metal, often platinum, on a plate. This layer is very small on the micrometer scale. These thermometers have different strain gauge effect based on what the metal and plate are composed of. Third is the wire wound thermometer. It gives stability to the measurement. A larger diameter of coil adds stability, but it also increases the amount of wire can expand, which increases the strain and drifts. They also have very good accuracy over a large temperature range. And lastly is the coil elements. They are similar to wire wound thermometers and have generally replaced in all industrial applications. The coil is allowed to expand over large temperature ranges while still giving support, and this allows for a large temperature range while decreasing the drifts. Next is I'm going to discuss about the basic RTD operations. But first, let us know again what is RTD. RTD is the resistance temperature detector. Its resistor is made from platinum, nickel, or copper. Platinum is the most common material due to its purity and consistency and predictability. It works by a small current sent through the resistor element and electrical resistance is measured. Also, resistance changes very predictability with temperature changes. Again, platinum is a standard of any other metals. The committees have adopted a mean temperature between 0 degrees Celsius to 100 degrees Celsius for industrial platinum RTD. Temperature coefficient of resistance, or also known as alpha. Its units are in ohms per ohm per degree Celsius. The formula in getting the temperature coefficient, or alpha, is equals to R100, which is the resistance at 100 degrees Celsius, minus Rs of O, which is the resistance at 0 degrees Celsius, all over Rs of O multiplied by change of temperature. And we all know that the change of temperature is equals to the final temperature minus the initial temperature. With that, we can get the change of temperature is equals to 100. With that, we can get the final equation of alpha, which is equals to R100 minus Rs of O all over Rs of O multiplied by 100 degrees Celsius. The relationship between resistance and temperature can be approximated by the Highlander-Van Dusen equation, which is RT is equals to resistance at temperature T is equals to Rs of O which is resistance at the ice point, multiplied by 1 plus AT plus B T squared plus C open T minus 100 degrees Celsius multiplied by T cubed. A is equals to alpha open 1 plus delta over 100 is equals to 3.9083 times 10 to the power of negative 3. B is equals to negative 10 to the power of negative 4 multiplied by alpha delta is equals to negative 5.775 times 10 to the power of negative 7. And C is equals to negative 10 to the power of negative 8 multiplied by delta beta is equals to negative 4.183 times 10 to the power of negative 12. But in positive quadrant, temperature over 0 degrees Celsius, C, is 0. So the behavior of platinum RTD simplifies to the equation RT is equals to RO open 1 plus AT plus BT squared.
What are thermocouple transducers? Thermocouple transducer is another type of temperature sensor often used in the industry. Thermocouple transducer is the most widely used to measure temperature based on the conversion of temperature into electrical signal. For us to understand its operation and basic structure, I have here a video found in the YouTube. A thermocouple is a sensor that measures temperature. In other words, a thermometer. It consists of two dissimilar metals which are joined together at one end and separated at the other. Usually, the metals take the form of insulated wires. The joined end of a thermocouple is known as the measuring junction. The separated end is known as the reference junction. When there is a temperature difference between the measurement junction and the reference junction, a tiny electrical current flows. When voltage is measured at the reference junction, the temperature at the measurement junction can be deduced. The relationship between temperature and voltage is a positive one. Increases in temperature produce an increase in voltage, and a decrease in temperature produce a decrease in voltage. Commercial thermocouples take the form of probes with the measuring junction housed in the tip. There are three main types of measuring junction: grounded, ungrounded, and exposed. The thermocouple wires in a grounded measuring junction are connected to an electrically conductive sheet. This means that the wires are in direct electrical contact with the substance whose temperature is being measured. Grounded measuring junctions provide fast response times but are prone to electrical interference. In an ungrounded junction, the thermocouple wires are electrically isolated from the conductive sheet. Ungrounded junctions are have slower response times than grounded variety but can be more reliable in some situations. In an exposed junction, the thermocouple wires protrude from the sheet and make direct physical contact with the substance whose temperature is being measured. Exposed junctions have a very fast response time but are prone to corrosion. For this reason, they are typically used to measure the temperature of gases. Thermocouples are available in many different combinations of metals and temperature calibrations. Each of these combinations is best suited to a particular environment and temperature range. Thermocouple combinations are denoted by single letter names. The four most common calibrations are J, K, E, and T. Thermocouples have a number of advantages that make them attractive to a wide variety of industries. They are durable, reliable, and inexpensive. In addition, they are compact and do not need to be electrically powered. Thermocouples have disadvantages too. The most important is that the electrical output they produce is very weak and has a non-linear relationship with temperature differential it reflects. This means that a thermocouple output signal has to be amplified and interpreted before it becomes useful. Thermocouple transducers are the most widely used temperature sensor, for it is suitable for measuring large range of temperatures. Its applications are widely used in manufacturing, power production, vacuums, and thermoelectric cooling, which include temperature measurement for kilns, gas turbine, exhaust, diesel engines, and other industrial processes.
Let us now consider a thermocouple as a vacuum gauge, as you see in the figure in the right. A thermocouple can be used as a vacuum gauge over a range of approximately 0.001 torr to 1 torr. The temperature detected at the thermocouple junction depends on the thermal conductivity of the surrounding gas, which depends in its pressure. Because of the thermocouple transducer's capability of handling very high temperature up to 2300 degrees Celsius, one of its most important applications is its extensive use in the steel and iron industries to monitor temperatures and chemistry throughout the steel-making process. Thermocouples are regularly used in the electric arc furnace process to accurately measure the temperature of the steel before tapping.
Hi, I'm Jonathan Singyan and I'll be presenting IC temperature sensor. What is an IC temperature sensor? An IC temperature sensor is a two-terminal integrated circuit temperature transducer that produces an output current and voltage proportional to its temperature. The sensor package has low thermal mass and a fast response time. It can be analog or digital. An example of IC temperature sensor is the LM35. An LM35 is an IC temperature sensor that can be used to measure the temperature with an electrical output proportional to the temperature in degrees Celsius. Why use LM35 in exchange for other sensors? Temperature can be measured more accurately than using thermistor. LM35 generates higher output voltage than thermocouples and may not require the voltage output be amplified. How does an LM35 looks like? This is the drawing of an LM35. The left side pin is connected to the source. The middle pin is connected to the output. The right side pin is connected to the ground. The output voltage of the terminal of the LM35 is proportional to Celsius temperature. Its gain factor is 10 millivolts per degree Celsius. LM35 does not require external calibration or trimming and maintains an accuracy of positive or negative 0.4 degrees Celsius at room temperature and positive or negative 0.8 degrees Celsius at the range of 0 to 100 degrees Celsius. It only draws 60 microamperes from its supply and possesses a low self-heating capability. LM35 comes from different packages. The TO92 or plastic light transducer, TO46 or metal can transistor light package, the 8 LED surface mount or SO8 small outline package, and the TO2 package. The electrical connections is presented here in this paper. This is the basic circuit diagram of the LM35. LM35 is this one. The left side pin a while ago is this one, which is connected to the VC or the supply voltage. The middle pin is connected to the output or this one. The output is parallel to a resistor. The resistor is grounded. The right side pin is this one. This is the basic. Integrated circuit temperature sensor. The advantages. Among all others, it is the most linear. The voltage and current is proportional to its temperature. It has the highest output. It is inexpensive. The disadvantages are the temperature of this LM35 ranges only up to 200 degrees Celsius, else it is not functioning well. Power supply is required. It is slow, self-heating, and limited configuration. Where can we see this LM35? Usually, they are used to monitor and control the temperature on circuit boards, the CPUs of a computer, in telecommunication applications like cell phones and PDAs, etc. Thank you for listening.
Good afternoon, classmates and Sir Ibarra. I'm Monique Lorraine L. Lamoca. I'll be discussing pyrometer. A pyrometer is a non-contacting device that intercepts and measures thermal radiation, a process known as pyrometry. This device can be measured to determine the temperature of an object's surface. So, the word pyrometer comes from the Greek word pyro, which means fire, and meter, meaning to measure. When temperature to be measured is high and physical contact with a heat object is impossible, radiative pyrometers are used. So, what are radiative pyrometers? These pyrometers measure the heat emitted by a hot object, and it is also a non-contact temperature measuring device in which they are used under conditions where corrosive vapors or liquid would destroy thermocouple, resistance thermometer, and thermistor. One advantage in using radiative pyrometer is its ability to measure very high temperature. Also, there's no need for physical contact with the object whose temperature is being measured. So I'll be discussing two types of radiative pyrometers: the infrared pyrometer and the optical pyrometer. So let's start with the infrared pyrometers. Infrared pyrometers allow users to measure temperature in applications where conventional sensors cannot be employed, specifically in cases dealing with moving objects such as rollers, moving machinery, or a conveyor belt, or where non-contact measurements are required because of contamination or hazardous reasons, such as high voltage, where distances are too great, or where the temperatures to be measured are too high for thermocouples or other contact sensors. All infrared thermometers function utilizing these basic design principles. Using various infrared filters, an optical lens system focuses energy to an infrared detector, which converts the energy to an electrical signal. This electrical signal is compensated for emissivity, typically manually, through linearization and amplification. In the instrument's processor, an analog signal is output. Electronics can be incorporated to convert the analog output to digital signals that can be transmitted at high speeds, allowing for extremely fast data acquisition rates. Ambient temperature compensation electronics ensure that temperature variations inside the infrared thermometer do not impact its output. Some applications with extremely hot operating environments can require water jacket cooling at the infrared sensor. Now let's proceed to the other type of radiative pyrometer, the optical pyrometer. An optical pyrometer is useful for measuring very high temperatures, even flames. It works by comparing the glowing wire of known temperature to the glow from a hot object. When the internal wire and the glow of the object are the same color, the temperatures are assumed to be equal. The temperature of the internal wire is controlled and known, and thus the temperature of the object can be inferred. As shown in the figure, an optical pyrometer has the following components: an eyepiece at the left side and an optical lens on the right, a reference lamp which is powered with the help of a battery, a rheostat to change the current and hence the brightness intensity, so as to increase the temperature range which is to be measured. An absorption screen is fitted between the optical lens and the reference bulb. A red filter placed between the eyepiece and the reference bulb helps in narrowing the band of wavelength. In an optical pyrometer, a brightness comparison is made to measure the temperature. As a measure of the reference temperature, a color change with the growth in temperature is taken. The device compares the brightness produced by the radiation of the object whose temperature is to be measured with that of the reference temperature. The reference temperature is produced by a lamp whose brightness can be adjusted till its intensity becomes equal to the brightness of the source object. For an object, its light intensity always depends on the temperature of the object, whatever may be its wavelength. After adjusting the temperature, the current passing through it is measured using by a multimeter, as its value will be proportional to the temperature of the source when calibrated. The change in current can be observed in three different ways. First, the filament is dark, which indicates that the filament is cooler than the temperature source. Second, the filament is bright. It indicates that it is hotter than the temperature source. Lastly, filament disappears. Thus, there is equal brightness between the filament and temperature source. At this time, the current that flows in the reference lamp is measured, as its value is a measure of temperature of the radiated light in the temperature source when calibrated. To end up, optical parameters can be used to measure temperatures of liquid metals or highly heated materials, and can be used to measure furnace temperatures. Here are some additional facts. Did you know that a hot air balloon is equipped with a pyrometer for measuring temperature at the top of the envelope in order to prevent overheating of the fabric? Also, a steam boiler may be fitted with a pyrometer to measure the steam temperature in the superheater.
Ba 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 na na, ba 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 na na, oh ba 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 na na, ba 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 na 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 na, ba 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 na na, とかりのポタトリカにマロマニカのティカババババナナ、よプラノフラマノノトマバナナラカモピタラモバナナバババナナポテトとかりのポタトリカにマロマニカのティカババババナナ